Okay, so in this video we're going to continue to talk about the Bohr model. Before we move on and talk more about the Bohr model of the atom, which by the way is the last model of the atom we're going to talk about, I just want to do a really quick example with Halflife, just because we covered Halflife a few videos ago. This question was actually taken from a previous IB exam. And if I'm not mistaken, this question was originally a multiple choice question on the IB exam a couple of years ago, but I've taken the multiple choice part out. So the question says the half-life of a radioactive element is 5 days. A freshly prepared sample contains 128 grams of this element. After how many days will there be 16 grams of this element left behind in the sample? Okay, so if you understand the concept of half-life, this is a very simple problem to do. Okay, so first of all, the half-life, remember, is defined as the time it takes for a radioactive element to decay by half, basically. So in other words, every 5 days that pass, you lose half of the previous amount. Now, by the way, before we move on, just to be clear, because this is exponential decay and it's not linear decay, it would be wrong to think, oh, okay, well, in 2.5 days, that means you only lose a quarter of the previous amount. That's not actually how it works, because the rate of decay is not constant, because it's exponential decay. Okay, so in other words, if you had a problem, with 5 days or 10 days or 15 days, that would be very easy. If you had a problem with like 9 days, which is not a multiple of the half-life, then it would be much more difficult to do, because again, the rate of decay is not proportional. And so you're never going to have a problem like that on the IB exam, at least not in SL physics. So anyway, we start off with 128 grams when the time that has passed. Okay, so I'm going to put mass over here. When the time that has passed is 0 days. Okay, so at the beginning of the problem, that's how much we have. Now, after 5 days have passed, we decrease by half of the previous amount, and half of 128 is, what is that, 64. 64 grams. After another 5 days, that is, after we're at 10 days in total, we decrease by half of the previous amount, we get to 32 grams. And then we get to 16 grams after one more half-life, which is 15 days. Okay, so we go through 1, 2, 3 half-lives before we end up with 16 grams of this element left behind. Now, keeping in mind that you don't have a calculator available to you on multiple choice questions on the IB exam, but this is one of those questions that you can very easily do without a calculator, as long as you understand the basics of half-life calculations. Okay, so now we're going to move on, so pause it here if you need to take a look at that one more time. Okay, so in the last video we left off with the postulates of the Bohr model of the atom, and here are the postulates that Bohr came up with. Now, by the way, a postulate is basically something that Bohr is just saying that you have to take as a fact with his model of the atom. Keeping in mind that because it's a postulate, you don't necessarily need to explain why these are true. You're just saying these things are true in my model of the atom. Now, we're not going to talk about any models past the Bohr model, but spoiler alert, the Bohr model of the atom is also wrong. It's also incorrect. But again, it's less wrong than the Rutherford model of the atom, which was less wrong than the Thomson model of the atom. Okay, so here are the postulates in the Bohr model. Number 1, an electron in an atom moves in a circular orbit about the nucleus under the influence of the Coulomb attraction between the electron and the nucleus, obeying the laws of classical mechanics. Now, this one is not really new. In the Rutherford model of the atom, the electron also moved in circular orbits, with the centripetal force being applied by the Coulomb force between the electron and the positive nucleus, and so that one is not really new. The second one, though, instead of the infinity of orbits which would be possible in classical mechanics, is only possible for an electron to move in certain orbits. Okay? In other words, the electron can only exist in certain orbits and it cannot exist in between. Now, the word that you might see it used a lot is the word called discrete. Okay? And discrete in this context, basically, you can think of it like a staircase. Okay, so if you think of the steps of a staircase, if I were to ask you, as you walk along a staircase, what is your height? Your height is either this value or this value or this value. It can't be anything in between. Okay, and so basically what he's saying is that the electron can only exist in certain discrete orbits. It can't exist in between. Now, why is that the case in Bohr's model of the atom? Well, that's not really important because it's one of his postulates. He's just saying, this is what it is. 3. Despite the fact that it is constantly accelerating, an electron moving in such an allowed orbit does not radiate electromagnetic energy. Now remember, that was one of the key issues with the Rutherford model of the atom. Because the electron is an accelerating charge, it should radiate energy and therefore should spiral into the nucleus. Okay? Bohr is basically postulating in his model of the atom that that doesn't happen. Now, the issue with that is, well, you still have the laws of electrodynamics saying that this thing should happen. So Bohr basically gets around it by making a postulate. In other words, he's basically just saying, the electron does not radiate energy, even though it's accelerating, because I say so. Okay, which is not really valid in science, but it is what it is. That's one of the issues with Bohr's model of the atom. So he's basically saying in my model of the atom, this electron is stable. It does not radiate electromagnetic energy, and therefore the atom is stable. Okay, and then 4. It says electromagnetic radiation is emitted. By the way, emitted, of course, means released or put out. And that word might make you think of emission spectrum, and it does have to do with the emission spectrum. Electromagnetic radiation, we are going to call, just for the time being, we are just going to call those photons. And we've seen the word photons before. Photons are particles of light. Okay, specifically they're particles of electromagnetic radiation, electromagnetic energy. There's a whole spectrum of electromagnetic radiation, everything from radio waves on down to X-rays and gamma rays. Okay, and so those little pieces of electromagnetic radiation that Bohr is talking about here, we're going to refer to those as photons. And basically he says in this last one that these photons are emitted if an electron, initially moving in an orbit of total energy E1, changes its motion so that it moves in an orbit of total energy E2. In other words, if it goes from one energy orbit to another energy orbit, if there's a change, then radiation is going to be released. Okay, the frequency of the emitted radiation is equal to the quantity E1 minus E2 divided by h, where h is a universal constant known as Planck's constant. We'll get back into the math later on. Okay, don't worry about any equations or math for right now. So we'll spend a lot more time on this 4th one later on. For now, I just want you to understand the concepts of the Bohr model of the atom. Okay, so pause it here if you need to write any of this down. And let's go on with the Bohr model. Okay, so the main points of the Bohr model. Okay, the Bohr model contains a nucleus, just like the Rutherford model of the atom, right? Because that's consistent with the Geiger-Marson experiment. Rutherford's model had issues, but it was right about the nucleus. Okay, in Bohr's model of the atom, electrons orbit the nucleus in orbits that have a set size and energy. The electrons cannot exist outside of these orbits. The orbits are discrete, in other words, and you cannot find the electrons anywhere else. The energy of the orbit is related to its size, meaning that the farther away you get from the nucleus, the higher energy level the electron has. I'll show you what that looks like on the next slide. The lowest energy is found in the smallest orbit. That is the orbit closest to the nucleus. By the way, the lowest energy orbit, or the lowest energy level, has a name, and that is called ground state. Okay, and it's called a ground state just like the name implies. If something is close to the ground, it has the lowest possible energy. Okay, so that lowest energy orbit, the smallest orbit, is called the ground state of an atom. And then this one that we're going to spend lots of time talking about, radiation. In this case, it's talking about photons or electromagnetic radiation, not alpha, beta, or gamma particles. That's something completely different. This is a different type of radiation. Electromagnetic radiation, that is photons, are absorbed or emitted. Keep in mind here it's saying absorbed or emitted. That's interesting. When an electron moves from one orbit to another. If an incoming photon has a certain amount of energy, it will promote or knock up, or what's another word of saying excite, an electron to a higher energy level. When an electron falls down to a lower energy level, it will emit or give off a photon. The energy of this photon is exactly the difference between the two energy levels. Now, we'll spend more time talking about what does that mean? A certain amount of energy. Basically, a certain amount of energy means this right here, the difference between the two energy levels. And in the last slide we saw it referred to like E1 minus E2. We'll come back to that later. Again, I don't want to do any calculations in this video. I just want to keep it conceptual. Okay, so pause it here if you need to write any of this down. Okay, so what does this look like? Well, Bohr's model of the atom looks something like this. You've got the nucleus in the center, and you've got the electron in circular orbit around the nucleus, and these dotted lines are the allowed orbits that the electron can live in, and it's not allowed to live anywhere else besides those orbits. Okay, so in the Bohr model of the atom, you have these set discrete energy levels. Let me just show you. This would be like the Bohr model of hydrogen, for example. You've got the nucleus, you've got one electron kind of going around. I guess Bohr's model, if you applied it to the entire periodic table, which you can't do, but if you did, the periodic table would look something like this. You can see how each atom has these electrons in circular motion, and there's these rings, and the electrons can only orbit along those rings, and they can't exist in between. Okay, now again, this is not very realistic because, well, we'll talk about why it's not realistic later. The Bohr model has its own issues. Okay, but that's basically what the Bohr model looks like relative to the Rutherford model, where the electron could be wherever it wanted to be. Okay, the idea of discrete energy levels was a brand new revolutionary concept at the time that Bohr came up with. It's not really tied to our day-to-day experiences. If you imagine lifting a ball up off the ground, the ball can have any height that it wants, right? It wouldn't make sense to say that the ball that you're lifting up has discrete energy levels because you can move your hand to any height above the ground that you want. And so this idea that electrons somehow have these discrete energy levels, that they can't exist anywhere besides those allowed orbits, is kind of a strange concept at the time. And really, the only reason people bought into it is because it happened to be consistent with the experimental evidence. Now, we'll come back to that in just a minute. The next slide says, note that all photons which do not have the correct amount of energy will pass through the atom. This explains why absorption spectra contains most of the colors. The only photons which the atom emits are the ones which have the correct amount of energy. This explains why emission spectra contain only certain discrete lines, and this model also settles the stability issue because, according to Bohr, electrons in these certain orbits do not radiate energy, even though it's just because Bohr says so. Now, what does that mean? Well, let's go back to the simulation. Here we have the nucleus in the center, and this orbit right here, this lowest energy level, this is the ground state. And right now we would say that the electron is excited because it is in an energy level above the ground state. Now, in other words, when the electron goes from this second ring down to the first ring, it is going to go down in energy. Now, because energy has to be conserved, the energy that the electron loses has to go somewhere, and it's actually released in the form of a photon. Okay, and so what we're going to see is I'm going to make the electron jump down from level 2 down to level 1, and when it does that, you're going to see a photon is going to be emitted. Here we go. Boop. There we go. Now the electron is orbiting in the ground state, and the only way for it to go up to an excited state, well, there's actually a couple different ways for the electron to become excited. It could be hit by an incoming particle, like another photon, or it could be heated up, or you can run electricity through it, and that'll give the electrons enough energy to jump up to those higher levels. Okay, but what we're going to see here is if a photon comes in with just the right amount of energy and hits the electron, boop, that photon can transfer its energy to the electron, giving it enough energy to jump back up to that higher energy level. And if another photon comes in with just the right amount of energy, boop, it can hit the electron and knock it back up again. Notice though, only certain photons are allowed to be absorbed because the electron cannot exist in between these energy levels. And so if the photon doesn't have just the right amount of energy, the electron's not going to absorb that photon at all. It's just going to pass straight on through. Now, it's also true that these electrons that are living in the excited state right now don't want to stay excited. They actually want to be close to ground state as possible. Just like when you drop a ball, its natural tendency is to go back to the ground, okay, back down to a lower energy state. And so this electron is currently excited. When it falls back down, it's going to emit a photon. And the photon it emits, again, it's based off conservation of energy. When the electron goes to a lower energy level, it loses energy, and that energy is emitted in the form of a light particle or a photon. Boop. There we go. In that case, it went from the third ring down to the first ring. It easily could have gone from the third ring to the second ring. And in fact, if the electron is sitting at, let's say, the third energy level, let me knock it back up really quickly, there's basically two possibilities for it to transition down, because it is going to transition down on its own. Either it can go from 3 to 2, or it can go to from 3 to 1. And in either case, a unique photon is going to be emitted with an energy equal to the difference between those two energy levels. Okay, now, what does all this have to do with, atoms and atomic spectra? Those photons that are emitted, that's where the emission spectrum comes from. Remember those lines that we see in the emission spectrum where we take a gas and we heat it up, or we run electricity through it, we see those set of lines. Each of those lines we see corresponds to one of these downward transitions, because when the electron goes back down, it emits a unique photon. So here we're going to see, boop, the electron is knocked up to the fourth energy level. When it falls back down from 4 to 3, it emits a photon. When it goes from 3 down to 2, it emits another photon. Okay, from 2 to 1, it emits another photon, and that's how we get this set lines. And so the Bohr model, for the first time, gives us a way to explain why emission spectra exist. Now, why do different elements have different sets of lines? Because the spacing between the energy levels is different for different atoms. Okay, if you think of hydrogen versus helium, the gaps between the respective energy levels are not the same, and that's why you get different photons that come out, aka different lines in the emission spectrum. So the Bohr model, again, gives us for the first time a way to explain the existence of atomic spectra. Now, we talked about emission spectra. What about absorption spectra? Well, if you send in white light, that is, if you shoot photons of every possible energy at this electron, most of them, 99.9% of them, are just going to pass through the electron, and the electron's not going to care. Some of them are going to hit the electron, and if they have the right energy, they're going to get absorbed. And guess what? If they get absorbed, that means they're not present when they come out the other side. That means they would be missing from what would normally be a continuous spectrum. That's why in the absorption spectrum you have those black lines. The black lines correspond to photons that got absorbed when they were passing through that gas. So Bohr's model is successful in that it at least gives us a plausible way to explain the existence of atomic spectra. Now, I'm just going to go through a few more slides and kind of show you what this looks like through the magic of this animation. Again, please feel free to take notes as you need. By the way, something I need to point out to you, the simulation we just looked at is wrong in one respect, and this is kind of important because I have seen IB questions about this before. In the Bohr model of the atom, what should actually happen with the electron energy levels is as you go higher up from the ground state, from 1 to 2 to 3 to 4 to 5, what should happen is the spacing between the energy levels should get smaller and smaller and smaller. And I don't think we saw that necessarily in the simulation that we saw a second ago, but that's how it should be. The higher up you go, the closer the energy levels should get together. Here we're seeing 7 energy levels, but theoretically you can go all the way up to n equals infinity. Now you might ask, how would you get to infinity? Well, remember the lines get closer together the higher up you go. And actually, let me just write this down because this is something you need to know. N equals infinity. That means when you go up like infinity orbits away from ground state, corresponds to ionization. Ionization. In other words, you get the electron so far up in energy level, it's literally fallen off of the atom, and therefore you have an ion. Okay, so n equals infinity corresponds to ionization. Okay, so that's just something you need to know. Now I'm going to continue clicking through the slides so you can see. Okay, n is called the principal quantum number. You don't need to know what it's called. You do need to know that n equals infinity corresponds to ionization, and that n equals 1 corresponds to the ground state. And everything above the ground state you say is excited. Alright, and most of this we've already talked about before. I just want you to be able to see the cool little animation that can maybe help you understand better than my words. Light energy is carried by a particle called a photon, that electromagnetic radiation that we talked about before. If the photon has just the right energy, it can be absorbed by, it says absorbed by the atom, but really it's absorbed by the electron, and stored by virtue of the electron jumping up to a new energy level. Okay, so there's the electron, photon comes in, zap, it can knock it up to a higher energy level. And then once it is excited, once it's at a higher energy level, it is spontaneously on its own going to fall down one way or another, either from, in this case, either from 3 to 2 or from 3 to 1. Here it says when the atom de-excites, the electron jumps back down to a lower energy level. When it does, it emits a photon of just the right energy to account for the atom's energy loss during the electron's orbital drop. So we've talked about that before. Now, this is a very common type of IB question to see. In this case, these horizontal lines basically correspond to the electron energy levels in the Bohr model. So E1 would correspond to ground state. And a very common question to see on the IB exam is how many different transitions are possible between these 4 energy levels. Okay, keeping in mind that a photon is emitted whenever an electron transitions from one energy down, keyword is down, to a lower energy level. Okay, so how many different transitions are possible? How many different downward transitions are possible? Well, let's see. We could have an electron go from n equals 2 down to n equals 1, and that would be one possible transition. And the photon that comes out would correspond to one line on the emission spectrum. What are other possible transitions? Well, we could have from 3 to 2. We could also have from 3 to 1. And if the electron happens to end up at the n equals 4 level, it could go from 4 to 3, 4 to 2, or 4 to 1. Sorry for my bad drawing. Okay, and so in this case, the answer to this question would be 1, 2, 3, 4, 5, 6 different transitions. Meaning if you were looking at the emission spectrum, you could see up to 6 different lines. Now, that's not completely accurate exactly. Some of the lines are not going to be invisible, or are not going to be visible to us, because actually some of the lines are going to be either in the infrared or ultraviolet part of the spectrum, which we cannot see with our eyes. But that's basically how you would answer this question. I've seen this question most commonly asked as multiple choice questions on the IB exam, where they give you, either 3 or 4 or 5 or 6 different energy levels and ask you how many different photons could come out or how many different transitions are possible. Okay, so that's a common type of question to see. Now, I'm just going to go to one more slide. Oh, and there's just the answer to the question. Okay, now here's where we're going to leave off in this video, the advantages and disadvantages of the Bohr model, and then in the next video we'll get into some calculations. The advantages of the Bohr model, it can explain why the atom is stable compared to the Rutherford model, at least more or less. And it can also explain the existence of atomic spectra. Now, it has some significant disadvantages. It cannot explain all spectra for larger atoms. It cannot explain relative intensities of spectra, meaning that some of the lines are actually brighter than other lines. And most importantly, the Bohr model does not give correct calculations for predicting lines for atoms which have more than one electron, which is actually a really big issue because, well, most atoms have more than one electron. Okay, and so even though it can work from a conceptual perspective, there's a lot of issues with the Bohr model, and so it was discarded, a couple of years after it was developed. But again, when you talk about science and building models on top of each other, the idea is that you want to be able to do more with each successive model and to be able to explain more phenomena. And so even though the Bohr model is wrong, it's less wrong than the previous model, which is how science should work. Okay, so in the next video, we're going to get into calculations and talk more about what that means, a certain amount of energy in the photon. I hope you found this video interesting. As always, please let me know if you have any questions, and I'll see you in the next video.